Welcome to my video. In this video, we're going to learn about mathematic logic. But before that, let me introduce myself. My name is Nimade Manika Prashanti with student ID 2413011063 and I'm from 4A class Mathematics Education. Moving forward, let's get started with the core presentation on mathematic logic. A statement is defined as a sentence that has a defined truth value. This means we can clearly point to it and say, yes, that is true, or no, that is false. In logic, a sentence cannot be both. It must be one or the other. Let's look at the example provided. Indonesia Raya is the national anthem of Indonesia. This is fact that can be verified. Therefore, its truth value is true. The next example is Bika Ambon originates from Ambon. This is an interesting example. While the name suggests it's from Ambon, it actually originates from Medan. Because we can prove this fact wrong, the sentence is a statement with a truth value of false. An open sentence is quite different. It is a sentence whose truth value cannot yet be determined. Why? Because it contains a variable or an unknown element that hasn't been defined yet. We see two types of example here. First, mathematic example. 12 times x plus 6 equals 91. We cannot say if this equation is true or false until we know the value of x. If x is one specific number, it might be true, but for any number, it's false. Because of this uncertainty, it remains open. Next example is social example. Sorry, I fell asleep last night. In a daily context, this is also an open sentence because it needs verification. Okay, moving on to our next topic, negation. After understanding what a statement is, we need to know how to flip its truth value. Negation is simply the opposite truth value of a given statement. In logic, we use the symbol not. If the original statement P is true, then its negation, not P, must be false. To make this easier to visualize, let's look at the truth table in the center. This is a standard tool in logic to map out all possible truth values. Example A, statement P, it is raining today. Let's assume this is true. The negation is it is not raining today. This automatically becomes false. Next, we learn about conjunction. A conjunction, symbolized as P and Q, is what we call a compound statement. This means we are taking two individual statements and joining them together using connective word and. The entire statement P and Q is only true if and only if both individual statements P and Q are true. Let's look at the truth table in the center to see how this works in every possible scenario. Row first, truth and truth. When both P and Q are true, the conjunction is true. This is the only way to get a true result. To make this crystal clear, look at the example. Statement P. A chicken is an animal. This is clearly true. Statement Q. Fish can fly. Generally speaking, this is false. Now, when we combine them into a conjunction, P and Q, we get a chicken is an animal and fish can fly. Because the fish part is false, the entire sentence is considered false in the eyes of logic, regardless of how true the chicken part it is. If a conjunction is an and statement, a disjunction is an or statement. It is symbolized as P or Q. The symbol looks like a V. The logic here is much more flexible than the conjunction we just discussed. A disjunction is true as long as at least one of the individual statements is true. As you can see in the definition window on the left, the only time a disjunction is false is when both statements P and Q are false. Let's look at the truth table. The last row, false or false. This is the only failing state. If both parts are false, the whole statement is false. Look at the example. Statement P. A cat is a mammal. This is true. Statement Q. The earth is cube-shaped. This is clearly false. When we combine them, P or Q, a cat is a mammal or the earth is cube-shaped. In everyday conversation, this sentence makes sound a bit strange, but in logic, this entire statement is true. Next, the implication. An implication, symbolized as P right arrow Q, is a compound statement often referred to as a conditional statement. In English, we read this as if P, then Q. An implication is only false when the first part, P, is true, but the second part, Q, is false. Let's look at the truth table. The second row, true, right row, false. This is the broken promise scenario. If the condition happens but the result doesn't, the statement is false. Let's take a look at the example. Statement P. Sarah uses an umbrella. Assume this is true. Statement Q. Sarah does not get wet. Assume this is true. When we combine them, P right arrow Q, if Sarah uses an umbrella, then Sarah does not get wet. Because both parts are true, the entire implication is true. Let's look at the most balanced relationship of all. A B implication is symbolized by a double-headed arrow. In English, we read this as P if and only if Q. If you look at the definition, the rule is very specific. A B implication is true only when both statements have the same truth value. Let's break down the truth table in the center. The first row, T, left right arrow T. Both are true. The result is true. Second row, T, left right arrow F. One is true, the other is false. They don't match, so the result is false. False. Third row. F, left, right, row T. One is false, the other is true. Still a mismatch, so the result is false. The last row, F, left, right, row F. Both are false because they match in their falseness. The logical relationship between them is actually true. Statement P. Cats can fly. This is false. Statement Q. Dogs have wings. This is also false. When we combine them into a B implication, a cat can fly if and only if a dog has wings. Logically, this entire sentence is true. Why? Because the condition for a cat flying is tied exactly to the condition of a dog having wings. Now that we've mastered the building blocks from simple negations to the balanced B implication, you might be asking yourself, when will I actually use this? The truth is, you are using mathematical logic every single second you interact with modern technology. First, look at computer programming. Every app on your phone is essentially a giant web of conjunction and implication if that. When you try to log in, the code checks if your password is correct and if your Face ID matches. Only if both are true does the then granting you access actually happen. It's also how we find information. When you use a search engine, you are using Boolean logic. If you're looking for a recipe but want to exclude a specific ingredients, you are using a negation, not to filter your result. In engineering, we use test connective to design safety system. Think of a smart home alarm. It is programmed as a B implication. The alarm sounds if and only if the security sensor is tripped while the system is in armed mode. It's a precise two-way relationship that keeps your house safe. Finally, beyond machiness, logic is a tool for critical thinking. It helps us take a complex political or marketing argument and strip away the emotion to see if the underlying structure is actually sound or if it's logically false. To wrap everything up, let's look at this summary table. This is your cheat sheet for mathematical logic. Instead of memorizing full truth tables, you only need to remember the critical condition that makes each connective false. First, conjunction. The symbol is P and Q. Connective and. When is it false? It is false if at least one part is false. Second, disjunction, symbolized by P or Q with connective or. When it is false, it is only false when both statements are false. Third is implication, symbols by P right arrow Q. If is, if blah blah blah, then blah blah blah. When is it false? Only when the first part P is true, but the second part Q is false. The last is B conditional or B implication. The symbol is P left right arrow Q. With connective if and only if, this is false when P and Q are different. Okay, that's all my video about mathematic logic. I hope you understand what I explanation for you. So keep practicing and see you in the next lesson. Bye!